In this video, we're going to take a look at the different types of equilibria that exist. This is just a surface covering of these different equilibria. There's a lot more than this. But the idea is that we're going to study equilibria that involve dissolving. So when you dissolve something, for example, if I take some solid silver sulfide and put it in water, the silver will basically dissociate into its ions. And then those ions will then reform the solid. And this kind of goes back and forth, and it keeps going back and forth until the rate of that back and forth is the same. And that's called a solubility equilibrium. So when your solution is saturated and you can no longer dissolve anymore, the reason that's happening is because your rate of dissolving, basically being dissociated into ions, and undissolving, basically going back into like the solid form, are now equal to each other. So that is called a solubility equilibrium, and we'll be studying that in a bit of detail in this unit. And so that is Ag2S solid. That's our example there. When you put it into solution, initially all of it kind of gets converted to its ion form. It already is in the ion form, really. I'm just balancing that here. But now it's dissolved in water. So dissolved in water means like aqueous there. And then we have our sulfur 2-. So those are the ions, and we simply got those charges from the periodic table. But the idea is that over time, these ions would recombine to form the solid form. And so there'll be a point where you've reached saturation, you can no longer dissolve anymore, you've dissolved the maximum, and that's when you've reached equilibrium for that. So that's called a solubility equilibrium. You can recognize it by just seeing that you're taking a solid, and then it's dissociating into its ions, so it's becoming aqueous, it's being surrounded by water. There's also phase equilibria, which is not so much, just like solubility is not a chemical change, it's a physical change. And that's where you have an equilibrium between two states. So for example, if I have water that's liquid and I decide to make it cold, so put it 0 below, it becomes H2O solid. And so that reaches equilibrium as well, where at 0 degrees, your water freezes and then melts essentially at the same rate. And that's called a phase equilibrium. We have an equilibrium between two states of matter. Same identity, but different state, liquid versus solid. And lastly, there's chemical equilibria. Those are basically chemical reactions. So if I have H2 plus I2, and they're reacting to form HI, at first, most of the reaction will be kind of the forward direction, the product being used up, or the reactant being used up, and then the product being formed. But then eventually, both rates will equal out, and we'll get an equilibrium happen here. Okay, but that's for chemical equilibrium is equilibrium for specifically chemical reactions. There's other equilibria we'll see. We'll see acid-base equilibria as well. So we'll see things called Kas and Kbs. Essentially, these different equilibria over here will have different letters next to them. So for the most part, chemical equilibria, we're going to see as Keq. Solubility equilibria we'll typically see as what's called KSP. And we'll see different types. We'll see acid-base equilibria. So an acid equilibrium will be a Ka. A base equilibrium will be a Kb. And essentially the unit's kind of divided up that way. So this first half of the unit is looking at just equilibria in general with a good focus on some chemical and some phase change equilibria, where you write equilibrium expressions, you calculate K values, and do a few general things like that. And then we kind of go in and we focus a little bit on the KSP stuff, so the solubility equilibria, and then a little bit on the Ka and Kb stuff as well. So we just kind of zoom into different types of equilibria. The last section of this note is basically just practice problems to help you review what you've seen so far. For the first set here, you can check your answers. It's included in the answer key provided, the filled-in version. You're just having to make some equilibrium expressions and then classifying these as either solubility, phase, or chemical equilibria. And then in our next question, you have a scenario where you have to determine the equilibrium constant and then determine what's favored based on that equilibrium constant. And if you want to find the answer to that, you can simply highlight on the document. but all the answers are provided online. I will go over one example from this just to show you what I mean by classifying the equilibria and making a equilibrium expression. So let's take a look at D over here. Okay, this one's quite interesting. You'll notice you have a gas and a liquid. So what you'll notice is that this is a phase change equilibrium. And so our KEQ is going to be equal to the concentration of that C2H5OH gas, the power of 1, over, we don't include the liquid. So you put a 1 in its place, but you don't have to write that 1 out. So you can simply write, that's your KEQ, just like that. I'm going to do another example. So I'll do example E here. Pause your video, try it first, and then unpause to see if you're on the right track. So this to me looks like we have a solid, and it's becoming aqueous, so it's dissolving. So this looks like a solubility. Solubility, equilibrium. So if we were to write the KQ, or you could say KSP. Right now I'm not too picky with that, but later I will be. You'll have your Na plus AQ times your Cl minus AQ. And we don't include the solid, so it's over 1, but you don't have to write it out. I'll try example C next, and again, you can check your work after. But essentially we have, it looks to me like this is not dissolving, and it's not a phase change. This is actually a decomposition happening, so it's chemical reaction. So we're dealing with a chemical equilibrium. And it's very easy to make the KQ for this. So we have your SO2 gas, and it's squared, times your O2 gas, and it's not squared, it's simply the power of 1, over the SO3 gas, and that's squared. There we have it. We'll try the last two. Again, pause and try it yourself. But the answers are all included in the main document for filled in. So here it looks like, again, we have a breakdown happening, not dissolving, but breakdown. So this is another example of a chemical equilibrium. And again, all gases, so we can include all these things. So we're going to get KQ is equal to concentration of H2 gas. And it looks balanced to me, so just make sure it's balanced first, times concentration of I2 gas over concentration of HI gas squared, because of the 2 in the front. Lastly, we'll do this one over here. Once again, it looks like a breakdown. So this looks like a chemical equilibrium. It doesn't have to be a breakdown. It could have been a synthesis or double displacement, so on and so forth. Chemical. And this is nice and simple. There's no coefficients in the front other than 1. So our KQ is going to be equal to Cl2 gas times PCl3 gas over PCl5 gas. And that is our equilibrium expression for that one there. So this was examples of classifying equilibria based on whether they are chemical, phase change, or solubility, and then making equilibrium expressions by remembering we do not include liquids or solids in our expressions. And this next example here, this last one over here, what you're basically doing is, again, pause the video, try it yourself, right? But you have an equilibrium mixture that has a mole of iron metal and this many moles of oxygen gas and this many moles of solid iron oxide. It's in a 2-liter container, and you want to calculate the equilibrium constant. And here's your equation here. So first step, remember, try it yourself, is KEQ. Notice, okay, interesting. I have a solid. I don't include that, so I make that a 1. Over. Okay, solid there too. Don't need to put that in there. make that a 1. So really I just have oxygen, O2 gas, to the power of 3. Now, it was nice I did this because I don't have to go calculate concentrations of the solid stuff at all, because I don't have to include them. I just include the gas. So my little side mission here, step 1.5, is concentration is equal to N over V. So for oxygen, it's going to be 1.0 times 10 to the power of negative 3 moles divided by the 2.0 liter container. And so if I go do that, I get 1 times 10 to the power of negative 3 divided by 2, 0.0005 molar. And then I can go and calculate my KEQ by doing 1 over the 0.0005 to the power of 3. So to the power of 3, 1 divided by that. And I get, let's try that again. I made a mistake in my calculator. So 1 divided by 0.0005 to the power of 3. And I get essentially 8. Let's see, sig figs are 2 sig figs, 8.0 times 10 to the power of negative 9. No need for a unit because it was a K value there. And we can go check our work. So just to show you once again how to check your work in these types of questions, you simply go to your document and highlight, and you can see 8.0 times 10 to the power of negative 9. So that in this video, what we did is we saw just a brief overview of the different types of equilibria. And then we went over some practice problems here, which you should try yourself before jumping into, before watching the video.